start this here. Yeah. Okay. So today for something a little bit different. So we have been. Yeah. Like this. Yeah. So today. So you filled that form, right, yesterday, that I asked you. I think I showed you the results in Slack, right? So you have an idea that you're not alone if you haven't finished all of the stuff, right? But then there's one direction that I could follow, that I won't follow, but I have made a tutorial for people because I know that especially for physicists, mathematicians, and so on, the analytical way of doing stuff like calculating the fixed points and calculating stability and so on, and learning a lot of SymPy to do that automatically and so on, has a very, very, very strong pull, okay? It's always attractive to try to do stuff that way, okay? But then this is harder to do. It's more complicated. It has some disadvantages, right? So, but I know that this pull is irresistible, okay? But then what I did is I wrote a tutorial on that, right? So I took, I think, the example from the other day from the bifurcation diagram exercise, and then I prepared a tutorial here for that stuff, right? So let me show you very quickly what I'm talking about. So this is in the links, but this is not what the class is going to be about today, right? So then let's quickly look at it. So you see that? So yeah, here it is. So this is, then I look at a slightly more complicated equation, right? Because, yeah, I could have done that with Rosenzweig-McArthur also, but I used this one that leads to even more complicated expressions than the other one, right? So, and then I do a bifurcation diagram of this system of two equations on B, right? This was what the exercise asked, right? Numerically and then analytically using SymPy, okay? But then there are a lot of trick things here in the middle, okay? That's why I'm not really going to do this in the class, right? And then at the end, after a lot of going back and forth, I get at a point here where I show that it's pretty much impossible. SymPy is not able to do this analytically, right? You cannot go all the way, like you can calculate the eigenvalues, but then you're not able to calculate the sign of those eigenvalues analytically, right? So you cannot really finish the calculation, okay? And then you have this what it is usually called the semi-analytic approach, where you go, there are several ways to do this, but usually you go as far as possible analytically, and then at the end you substitute values of parameters to plot stuff, okay? So this is, but this is simple when I thought like that, but then if you go, for those interested, if you go through the tutorial, it's more involved than it first looks, right? So I set values of parameters, and then there's a lot of, there are a lot of tricky things here in the middle, okay? But then I get to this, I get to this plot here, which is pretty much the same as the first one, except that I don't have the cycles here. I only have that this fixed point that was stable now becomes unstable, and this means that there will be cycles, right? But you cannot really see the cycles, okay? Because the cycle is not a fixed point. How do I analyze something that is not a fixed point? There are a few tools, but it's hard, okay? It's hard. Usually they are only useful here very close to the bifurcation, not for any period, okay? Okay, so, and here, this is where I wanted to get, right? So the pros and cons, okay? So the numerical method, this is what you are really going to focus from now on, because it's more general in the sense of, you pretty much always can do bifurcation diagrams and exploration parameters completely numerical. Just solve the solution, solve the equation for one parameter, and then another, and then another, and then another, and so on and so on. And this works fine. The only problem with that is it's computationally expensive, okay? Because for each set of parameters, you have to run the simulation, and then you change parameter, run the simulation, change parameter, run simulation. So you don't have an expression where you given a set of parameters, you already know the stability. Now you have to simulate. Okay, so this is much more expensive computationally, but it's kind of a straighter route. Okay, so it's pretty much always possible to do that. It's and even when it is expensive, we will see that there are some ways to try and make this more efficient, right? So we can try to be smarter about, I don't know, running time. We maybe use parallelization, use stuff like that to speed up. Okay, but the only more negative part about this is that you only see one stable solution at a time, right? So I think Roberto is going to talk. Well, you have seen a bit of bistability already with the competition loss of Volterra model, right? But when you have more problems arising from bistability, right? So this gets a bit more complicated because then you're not sure if maybe there's another stable solution that you're not seeing because your initial condition is close to one and not the other, and so on, right? So this is a bit trickier, right? So this is the only real negative here, okay? That in order to overcome this, you really have to look carefully at your system to check if there's bistability or not, okay? But then for the analytic method, okay, the analytic method, if you get to the end of the calculations, you have the full picture ahead of you, right? So for any parameter value, for any initial condition, for any, you know already the full picture, okay? So this is very impressive, but then you only do that for a few restricted systems, right? For most systems of equations, you don't get to go to the end of the calculations, right? So if you have, for instance, a system with three equations, now your eigenvalues will be the solution of a cubic equation, usually, right? So cubic equation, well, unless one of the solutions you already know, for some reason, we'll have roots that are very, very complicated and so on, right? So for three or more equations, it's pretty much always a mess. Even for two equations, sometimes it is a mess, as in the example that I showed here, right? So, it's rare that you can carry the calculations until the end, right? And if you don't carry the calculations until the end, you have the semi-analytic method, okay, that you can compute efficiently for pretty much any parameter set, but it still has this issue of you can't analyze periodic solutions, right? Only fixed points. But then it's very complicated, right? So it's complex to implement. If you're not familiar with the calculations on pen and paper, right? Doing this with SymPy will not make them a whole much simpler because you have to look at the expressions and get more or less what is going on, right? So if you don't do a lot of calculations yourself, right? It's not that SymPy is so smart that it will make the algebraic calculations for you, but it will not it will not interpret the expressions and do the thinking for you. You see, so it's you still have to have a feeling for the expressions and what to do with them and so on, right? So usually you have to look at the expressions to see what to do later with them, you know. So it's not like completely automatized. It's not like it just has a general function that always spits out the whole solution, right? You have to go fixed point by fixed point, check which signal you can, which eigenvalue you can already determine the sign or not, and so on, and recognize that this expression also shows up in the other eigenvalue as well, and so on, right? So if you read this tutorial, I think the difficulties become clearer, okay? Okay? So all of this, just say, this is very interesting. I know some of you will want to read this and understand this. It's kind of unavoidable. But then I won't go into it, okay? Yeah, is that okay for you? Yeah? Okay, so what do I want to do now then, right? So now what I want to do is, okay, a lot of you told in the forum that you haven't been able to finish or to understand very well the tutorial on bifurcation diagrams, okay, the exercises on bifurcation diagrams. And I think this is really worth our time to go through, okay, because I think it's gonna be very useful in your projects and through your life, you know. So, so I think this is very fundamental, and so that's the one I'm choosing to pick up and try to solve in class, right? For the others, right? So especially for the beginning, the ones right in the first week, right? The tutorials on Python, NumPy, and so on. A few of you got stamped or didn't finish, right? So what I'm going to do, I think, one way that we would proceed is to use Slack for that, right? So Slack, I think for this kind of stuff, it's useful to have because Slack works like a chat, right? So it's everything in the same channel, okay? But maybe I think there's something called the circles. Do you know what I'm talking about? Inside channel. So you can make it work more or less like a forum, like you have threads for specific topics. So I will create a series of topics inside a channel, and so one for each. I don't know if each exercise or at least each of the classes, right, that have exercises, and then we can share some plots that you have made and share questions. And I think then we can either go over questions if you have done, or go over or give tips for if you're stuck, right? So I don't think several of you asked it for solutions of the exercises, but I could do them, right? So it's not a big trouble, but then I don't think it's very useful either, right? Because once you have read how to do it, okay, then it becomes kind of obvious, right? But really, the point is not to see how it is done, but to work on your skills to get it done, right? So it's so maybe sometimes just a small tip. Okay, think about this. It's better than, oh, here's the solution. You see what I mean? So so I'm trying to avoid sharing the full solution. Okay, yeah. Okay, because then for you to train, I have to provide you with more exercises, you see? Because that's the way you improve, with more exercises, not with the full solutions, okay? Does that make sense? Do you disagree, or are you okay with that? Sorry, do you have comments? Okay, yeah? Okay, people. Then, okay, then for today, let's go back to bifurcation diagrams, okay? Yeah? Let's see. So this one here, right? So bifurcation diagrams. It was this one over here. Okay. This one. Yeah. So you remember then that the idea was that we were going to pick a parameter here. Okay. In the case that we did in class, we had the Rosenkreuz-McCarthy equations. Okay, I'll make a copy here. So, yeah, something that I should have told you is that if you want to change and save the changes, you have to make a copy, right? I think a lot of you have lost some of your annotations during class due to that, right? So if you just click the link and change something, when you turn off the browser or the computer, when you go back, you don't have your changes anymore, right? So I'm going to make a copy over here, okay? So yeah, here it is. So this is the copy. And what's the idea? Is that, for instance, we are going to change the carrying capacity here, right? So the idea is that we go over many values of carrying capacity and record the solutions, right? And record the solutions, and then we are going to plot the solutions as a function of the carrying capacity, okay? These solutions can be either a fixed point or for a high value of k, they become oscillations, right? And then instead of plotting the full oscillations, I have to run everything here. So let's go step by step, right? So first, I have this situation here where I have a stable fixed point, and then I plotted the phase space with the arrows. Now for a larger k, I have oscillatory solutions, and now the phase space looks like this. Okay, and now I'm trying to plot this diagram, okay? with only 2 points. And you see that instead of plotting the whole solution here of the oscillation, I plotted the minimum and the maximum, okay? So I see the amplitude of the cycle, okay? The minimum maximum for the predator and for the prey, right? And then I have this stuff here, okay? This is something that has a very specific structure that is really useful to, like, once you have seen this once, right? It's a very common practice to just copy and paste and then modify to your needs, right? Instead of having to write it all over again, right? So usually you have to save the values that you want to have later, right? So the minimum and maximum, okay? You have the range of the parameters, and then you set the times that usually have to be large in order to arrive at a stable point, right? So that you ignore the transient. Do you remember all this decision? Or, yeah? More or less, yeah? Okay, and then you go for each k, you change the parameter list to include that k over here. You run again the simulation, and then you take the solution and you look at the end of the solution here, right? So only the last 1,000 points here. I had 6,000 points, right? Something like that, yeah. Over here, yeah, 6,000 points. Now, and at the last 1,000, and I take the minimum and the maximum, all right, for both prey and predator, and append it to those lists, and at the end I convert these lists to arrays for ease of manipulation, right? So, and with that, this already takes a bit of time to run, right? So this is what I told you, that this is computationally expensive, okay? This is for a single parameter. With more parameters, it will be even harder, right? And then I just plot this as a function of k, okay? So I have here a stable fixed point, and then from this value of k onwards, I have a bifurcation to cycles, right? So I have here limit cycles, okay? Okay, so questions so far? Comments, things that were not clear? When you came back to it later, you are not so sure you understood, or the issues are mainly solving the exercises themselves? Would you prefer to have a little bit more time to try to solve them again, or do I just solve it together with you? Sorry? Together. Okay, let's do it then. Okay, so here, so let's try to do some exercises then. Okay, so the first one is this model for a sterile in situ release, okay? And then you have this large N, capital N here, that represents the population of this insect, okay? Usually a pest or a disease vector or something like that, okay? And you see that if N, before going into that, you see that if N is equal to 0, okay? If N is equal to 0, the small n here, that is the number of sterile males that I insert in the system, okay? That I keep in the system, right? I'm saying I'm keeping them, I keep always this level of sterile males in this population. It is a bit weird, but okay. I see that they influence the birth, you have here the birth rate, the death rate, and here you have a loss due to competition. And you see that this, for n equal to 0, this n cancels with this, and here this becomes just a, right? So this is a constant birth rate, right? So if this is 0, this n cancels out with this n over here, right? And then I just get a. And a minus g is the R, right? The intrinsic growth rate, okay? And then also here, the small n here also affects competition, right? So usually you have a constant times n squared for competition, interspecific competition, but now the small n also affects competition, okay? It also increases this competition. It competes with the other ones, okay? Okay. But this is from a mathematical perspective, I don't have even to understand this, right? But it always helps us to understand a bit the equations in order to analyze them. Because, for instance, I told you that if n is equal to 0, this reduces to a, right? And a minus g is r. So the population can only grow if a is larger than g, okay? Otherwise, the population growth is, the intrinsic growth rate is negative, the population always dies out, right? So to have some chance of having something interesting, I have to set A larger than G. Okay, I told this already here, but this is why, right? This is why, okay? Okay, so, so what do we do then? The first thing is, okay, we want a bifurcation diagram, but before having a bifurcation diagram, I have to solve the equation, right? So don't go directly to the bifurcation diagram. Solve the equation for some set of parameters first, see that it goes to a fixed point or something, and before going to the bifurcation diagram, you see? So let me copy the header of this part here, yeah, so this part over here, yes. Just so we can run this even without, yeah, are you following along, or is that kind of, yeah. Unfortunately, we can't do this together in the sense of plotting, changing here and immediately changing on your computer, right? Because we not really edit them at the same time, right? Okay. Now I want to define a function. I'll call it sterile, right? That receives x and t. X here is just my n, right? I would even call this n. Okay, this is not a problem. Okay, this would be n also. Right, and then the parameters, right? Which are the parameters? A, G, N, small n, right? So you see that small n is not a variable, it is a parameter, okay? It is fixed, okay? Yeah, so this there's only one dependent variable here, that is the large n, okay? Okay, so we have then the parameters, they are A, G, small n, and the competition parameter C over here, okay? So this 4 parameters, okay? And now, this is a single equation, so I don't need to return an array. I can return just a single number, okay? So I will return. I have to write down this expression over here, right? So A times n divided by n plus n over here, and all of this minus G, all of this times n, okay? All of this times n, and then the other term, okay, minus c times n times n plus n, okay? So far so good? Yeah? Okay? Okay. Okay, so this is the equation. Now I need what to solve this? I need a set of parameters, right? So instead of doing one by one, I just set them in order here, right? So, but to do that, it's nice to remember to keep the order close here, okay? So, yeah. So the list of parameters here will be, which will be A, G, so A, G, N, and C, okay? Now becomes a question that is kind of funny, right? Because I just told you, well, A is larger than G, and I didn't tell you anything about any of the other parameters, right? So this is a bit confusing already, right? Because, well, what parameters do I put over there? Yeah, I had to choose, well, I'm going to vary small n, okay? This is going to be my bifurcation diagram, okay? But what do I choose for A, G, and C? Right? Does it matter or not? Yeah? So, so you see, this is already something where having a bit more experience with this kind of model helps, right? So, you see, Roberto did he told you something about something called addimensionalization? Addimensionalization, did he tell you something about that? No? Or he thought about it but didn't go into details over how to do it, perhaps. But okay, but you see that, whenever I have a model, right, I have something that is a model like this, right, for population. I have a time scale, because there's time here, and I have a population scale, okay? So you see, there will have to be some parameter that is related to time, usually a growth rate or a death rate, that more or less fixes the scale of time. And another parameter that has something to do with population density usually a competition term or something like that that fits its population scale, okay? And then this is what is going to happen here. So A is going to be a growth rate, okay? It's a growth rate, and G is a death rate. So either A or G is going to fit my time scale, okay? So since it depends on the time scale, you can just say, okay, I'll just put A equal to 1, yeah? Because it doesn't matter. It will be 1 in some unit, yeah? 1 per month, 1 per 10 days, 1 per year, whatever, okay? So the only real free parameter here is G, that is the death rate compared to the birth rate, okay? But this I already know that it should be smaller than A, right? So then I can choose, I don't know, do I want to have a high death rate? So I don't know, G close to 1, so I put something like 0.9. Or do I want to have a large growth rate? Then G is, I don't know, close to 0, right? It's 0.1 or something like that, yes.
Can you repeat, please, what are the three parameters?
Sorry?
I did not follow what are the three parameters.
Yeah, A, as I told you, A is the birth rate and G is death rate, okay? Yeah, from the model, right? But then A, one of them, they both are rates, okay? So they are defined in terms of like A of time, okay? If I have, for instance, 1 birth per year, this or 1 birth per month, this is 12 per year, or this is 0.03 per day, right? So it depends on the unit you use, right? So since you are always free to change the time scale, whenever I have this, I can, one of the parameters related to one of the rates, I can always go and set it to 1. Because in some unit it's going to be 1, right? Yeah? You don't know the unit, but it doesn't matter, okay? So you only have to choose something for G, okay? And G, then this is a yes. This is really a yes, okay? And is that clear? Yeah?
Yes. And the other two parameters, they do not have times.
Yeah, well, G is also a rate, so it's also measured in time, yeah?
And C?
Well, C will also have time inside it, yeah? But then it's also having to have population density because it's a competition term, right? So it's also going to be free because it measures something related to density. If I measure populations in terms of grams or kilograms or individuals or thousands of individuals, you see, so it's also a bit of a free parameter, okay? So I have to choose G, okay? I'll choose something like, I don't know, half, right? Because this is smaller than 1. Could be 0.9, it could be 0.2, it could be 0.3, okay? We can change this later, okay? But knowing that at least one of them related to time is completely free and I can just use 1, right? Already makes it easier to choose stuff, yeah? You don't have to worry if I choose 10 or 9 or 8 or whatever. You just set it to 1 to be simpler, okay? Does that make sense, people? So this is a tip that is kind of a pro tip, okay? just to make it easier to, when you don't have, of course, if you are in a specific problem where you already have parameters, okay? You go and use those parameters, of course, yeah? If you already have from the literature those parameters. But if I just exploring a model, I'm free to set some parameters to 1 because I know that in some scale of time and population and so on, there will be 1, okay? Yeah, questions? So far, so good? Okay, and then there's n, okay? N is the parameter that I want to vary, right? So at first, I'll put it to 0, okay? I put it to 0 here, right? Because this is the start, okay? I put it to 0, and the competition term, as I just told you, it could be 1, right? Because it could be anything, depends on the population scale, okay? Depends on the units that you choose to for measuring our population density, yeah? So I can set it to anything, it doesn't matter, okay? Now, with that, now I have to have time, okay? So time, I'll set on a range here, I don't know, 0 to 50 or something like that. Usually, this is a bit hard to guess, right? So I usually look at the plots and see if I need more time or less time, right? So this is also why it's better to do the simulation before doing the bifurcation analysis, because then you see if you're using a long enough time, right? Yeah? Okay. And finally, I need an initial condition. I don't know exactly where to put it. I'll put it, since I have everything set to 1 here, I'll put this at a low value of 0.1. Right, and now I go OD int with sterile over here at 0, t, and the list of parameters, okay? Yeah, so this is easy, right? So this is just using the function, right? And then I'll take this and plot, okay? So ts over here, right? I will put a label here. This is, oops, this is time. Oops. This is time. And this is population, okay. Maybe some grids also, right? I like grids, yeah. Okay, so let's run this. Oh, there's some, over, yeah. No, what did I do wrong? A, G, and C, 1/2, 0, 1. Extra arguments. Oh, okay, this should be a tuple, not a list. Okay. It should be like this. Okay. Yeah. So you see, we have here the population starts at 0, 1. It grows and saturates at something that is like a turn capacity. Okay. So you see that the time range that I chose was okay. 50 looks okay, right? And now let's increase a bit the value of, so this is what, so we saw something that made sense, okay? It just grows to current capacity, right? What if we increase it n, right? So this is what we're going to see with the bifurcation diagrams, right? So if we increase n, so it is at 0 now. If I increase it to 1, does it make a difference? Well, here the population already went to extinction, okay? Why? Because, let's go back here. Why 1 is already too much? You see that 1 is already too much. 1 already goes to extinction. Why? Because with 0, the turn capacity was half, right? So 1 is double this earning capacity already, right? So y is already very large value. So yeah, so if I put half, that is the earning capacity, probably already has extinction, right? Yeah, already just extinct, right? So what, if I'm going to look at the bifurcation diagram, what is the range of values of small m? From 0 up to at most half, okay, at most the earning capacity, right? Which is already a bit too large, right? Because it's funny that you are able to have as many sterile males as the whole population of insects, okay? This is a huge amount of insects usually, right? So yeah, okay. So this is an initial exploration. It's important to do your bifurcation diagram, okay? Without that, you don't know what are the range of values, what is the time scale, and so on, okay? Yeah? Okay, so then let's do now, I'll open another cell over here, oops, to do the bifurcation diagram itself, right? So what do we have to do? So let's just copy and paste this here, right? So just so we yeah, this is stuff here, so we can work on the, do you think this is easier than typing everything again, or not? Yeah? Yeah? Or does that count as cheating? I don't know. Okay. So, yeah. So what do we need? We need the minimum and maximum again, right? Of course, I'm doing this. I know here that in this system here, I shouldn't have cycles, right? But maybe, right? So let's do this with minimum and maximum also, right? And now the values that I want is not the values of k, it's the values of small n, okay? I will start at 0. I go up to 0.5, right? With which time step? Which step here? So usually to have a nice plot or something like that, you need something like at least some 50 points, right? Yeah, 50 points. So maybe 0.01, right? So it's, if you take a much smaller value, the plot will be smoother, but then it takes a lot longer to run, right? So usually 50 points for our first plot is okay, all right? So if your simulation takes too long, you maybe use 30. If it is too weak like this, it would put 100, and it would be okay still, all right? Yeah. Okay, now the time step. So I use it this here, I use it 50, and it looked at very okay here, okay? Yeah, very okay. But then, just to be sure, let's put double that, okay? Right, so let's put 100 time steps, okay? Time going up to 100, and now the initial condition is not an array, right? I'll put 0, 1 here. Okay, and then I do the loop over here, okay? Let me delete these comments here to clean up the old a bit. I don't know if you, at least change a bit here. Okay, now the new n over here. So now I have to use the parameters for this equation here. That is this set of parameters. I'm going to copy also. You see, that is nice to organize it like this. You see, I really like this. So that you don't lose track of which value is each parameter, you see? So I up it here, right? And now the difference is that the n value here is not half anymore. It's going to be the n of the loop, you see? For n, small n, in the array, in this array over here, okay? I delete the old one. And then this is just the integration, right? I just integrate this equation. This is the sterile equation. Equation with y0, time, and the parameters here, okay? And now, what do I want? Here now, the y has a single value, okay? Because this is a single equation, right? So I don't need the second index over here, okay? So I just take, and how many points do I want, right? So the time here, there are 100 time steps, right? So I saw here that after time 50 is already okay, but then I would just look at the last, I don't know, 30 points, probably okay, right? Yeah, after 70 time, after a time of 70, I look at the last 30, right? Does that make sense? Yeah, so here, instead of 1,000, I just add the last 40 points. And the minimum, I don't need this axis equals 0. It doesn't matter here, but because there's no second axis, okay? Because it's a single equation, right? Like this. And then the same here for the maximum, okay? So I adapt the other one just like this. Epsilon max takes the max over here. Okay, and I can delete this, I convert it. Okay, good. And now, yeah, it already ran, you see, it was pretty quick, okay? And I just plot it, okay? Let me plot like this, right? So, yeah, let me take this plot over here. Now I plot NN here. I don't need the second plot, okay, because this is a single equation. This is n in the, yeah, and then this is y min. This is just y min actually, because this is a single array, okay. You don't need the zero or the column 0 because this is a one-dimensional array, right? Yeah. Okay. Maybe we would have another cell here just to be sure of that, right? So let me print y min and to see what it looks like. Right? So you see, it's not a bidimensional array, it's a single array, right? And a one-dimensional array, because this is only a single equation, right? It doesn't have two columns, it has only a single column, okay? So I don't need to use to take the first column here, okay? And I don't need a legend either, so I don't need this label. Yeah, okay, and I just plot this. There's some error over here. Well, I use a KK here. It should be NN. Okay. Yeah. Okay, so here it is, right? So it starts here at 0. The population is at the carrying capacity that is half. As I increase the value of m, it keeps going down, down, down until around 0.07 here, it collapses, okay? And then I just have 0. So you see that going up to 1/2 was already too much, right? I would stop at 0.1 actually. Yeah, question?
Can you solve the equation again with n equals 0.1? Just to check that it
Yeah,
goes to
exactly. This is a good idea, right? So if you see that this is 0 over here, right? So let's go back to the first one over here and put 0.1 here, right? Instead of 0.5, okay? With 0.1, the population is already synced, okay? Yeah? Okay, so maybe let's redo the bifurcation there because this is kind of weird, right? Going until here and see here that this is a big step, right? If I plotted this with points instead of lines, okay, you would see something, oops, a bit weird. Oh, I put a comma instead of a point. Sorry. This is kind of a large step here, right? This is not so nice, right? So to really be nice here, we have to go with n only up to 0.1, and here I can take more smaller steps, right? So 0.001, right? I run this again. I plot this once again. And now it's nicer, okay? You see that this is really abrupt over here, you see? Yeah? I would expect perhaps we would expect something to be a little more smooth over here or not? Don't know. Maybe let's try again, right? So maybe stop at 0.06 and go in smaller steps, yeah? Since this is going fast, so yeah. Well, there is a point over here, right? But then this point here leads me to believe that perhaps it is not so abrupt, right? But yeah, maybe it's, anyway, it should be quite abrupt, but maybe it is doing this, I'm not sure, yeah? I have to do more analysis here, but you see that we already have a general shape. It's the carrying capacity or the equilibrium population is going down slowly, but then at some point here it falls abruptly to extinction. So there's a value here that is a little bit above 10% of the carrying capacity, where where the population is extinct, it collapses. Okay? Nice? Yeah? Questions, comments, or I don't know, something that you see that here I actually did like 10 bifurcation diagrams. I did the first one, and then I chose a different range to see better. Then you keep this is a presentation matter, right? So it's not there's one single bifurcation diagram that is this solution, right? It's not there's this solution. It's a presentation issue, right? So which range do I want to focus on? Do I want to zoom in on some region or not? Do I want to, you see what I mean? Yeah? So you can go and measure, change it a bit until it looks something that it's easy to understand and to explain, okay? Questions, comments, everyone is okay with this? Everyone is with me, yeah? Yeah? Okay? Okay, so for the second one then. The second one is the real challenge, yeah? Okay, let's do that. Yeah?
Do we have to, when you showed the solution during the class, you did something about the initial condition,
Yeah.
where it would take the last point from the previous solution.
Yeah.
Do we have to do this on this case?
This is an issue that this is a peculiar problem when you have bistability, right? If you have bistability, it's a good idea, but only if this bistability doesn't include the zero, right? Because the problem with this is that once you reach zero, then if you put zero as the initial condition in the next step, then it's always stuck at zero, right? So this is an issue with using the solution of the last simulation, okay? Especially, for instance, in this thing here, right? This is a predator-prey. the second one, right? So at the very beginning, right, with b equals to 0, right, so with attack rate equals to 0, what is going to happen to the predator? It's going to collapse, right? It's going to go to extinction, so it will be 0, right? And then as you increase b, right, and if you use the previous initial condition, it's always going to be 0 because it's already starting at 0, okay? So then that's not a good idea in this case, okay? So it's, in some situations it is useful, but it's not like you should always do that, because if you always do that in some situations, you get stuck at a fixed point that is not the fixed point you want to explore, okay? Okay. Okay, let's go for the second one, yeah? Second one, so again, we don't start directly with trying to go for the bifurcation diagram. We start looking at the model and trying to understand a bit the parameters and the equations, okay? Then we solve the equation for some set of parameters, look at the solution, and then see if this looks like a reasonable set of parameters, and then we go for the bifurcation diagram, okay? Okay, so let's look at the equation. So this is consumer resource equation, predator-prey equation. The resource here, the growth rate of the resource is a logistic growth, okay? And then for the consumer, I have a death rate here, okay? And then there is this term here that is the consumption term, right? So this is proportional here and here, okay? I think in the last version, I changed this E for, no, in the other notebook, not this one, okay. Yeah, but it's helpful to do this here also. Oh, no, let's leave it like that, so it doesn't matter. Okay, but then this functional response here has a very strange shape, right? It's 1 minus an exponential and so on, and there's no error multiplying here. It's kind of funny, all right? It's kind of funny, okay? But it's still, right? So if b is 0, what happens when b is 0? This is the exponential of 0, right? Then 1 exponential of 0 is 1. And then I have 1 minus 1 is 0. So the consumption rate is 0, right? So if b is 0, there's no consumption, right? As b increases, this exponential is a negative exponential, so exponential decreases, and then you have 1 minus something that is less than 1, right? So then I have a positive number inside parentheses here. It means that consumption rate is increasing, right? So b, that's why b can be seen as a kind of an attack rate or a predation rate, okay? Yeah, an attack rate, right? So something like that, okay? Okay, so what do we expect also, right? So again, we have R. We will have always some growth rates and death rates, so I can either set R or G to 1 to fix the time scale, okay? And I can set, for instance, carrying capacity to 1, because it sets the scale of population density, okay? I have some parameters that are really, really arbitrary, okay? So I can just set it down to any value, okay? Doesn't matter. Okay, then what do we have to be careful, right? Exponential, this is always positive, right? So the maximum value of this stuff inside the parentheses is going to be 1. Right? Yeah, the maximum possible, right? Yeah, because even if b is very, very large, this exponential here is going to 0, okay? So the maximum value here is 1. So if predation rate is the maximum possible, right? Population for C is going to be minus G times C plus E times C, right? So if G is larger than E, right? The consumer is always doing it synced, right? The growth rate is always negative. You see what I mean? Yeah, so that's why I set here, say here to set that G should be smaller than E, so that for a large enough predation rate or attack rate B, I have that the consumer can increase, okay? Does that make sense? So you see that I already have some relationships between the parameters, even without running any simulation, okay? So it's nice to be able to think a bit about the model before doing the simulations, okay? Now, let's go for the simulations, right? So let me once again copy, I'm trying to copy this here to have them to be independent, right? Each part of them. over here, and now I'm going to define, although this RC is a general resource consumer model, okay, I don't know any name for this equation, right? So I tell this, it will receive an X that is an array with the values of R and C, okay, T, and then the list of parameters, right? So there will be R, K, then there will be A, B, over here, then G, and then E, okay? G and E, okay? Okay, and then I write down the equations, okay? So I have to return an array with two values, okay? The first one is going to be, okay, let's write it like this. So R times the resource that is at 0, okay? The first one times 1 minus R that is at 0 over K, right? Okay, minus A times C that is x1 times 1 minus exponential, and exponential is np dot xp, okay? Here it is getting already too large here, okay, to fit in the, so I'll break this, okay? I'll break this like this, okay? I hope this works, yeah. Usually when you have an expression that is inside a bracket or a parenthesis already, you can just break line without worrying, okay? If you had something like this, x equals to 1 minus 2, this doesn't work, okay? But this works, usually, okay? Yeah, so if you are already inside a parenthesis, it knows that the line that is broken has to continue the next line because there's a parenthesis open, okay? But if you don't, then it doesn't work, okay? So this is useful when you have a large equations like this. So minus then, minus A times C that is x1 times 1 minus exponential of minus B times R that is at 0, okay? So this is the first term here, the first equation. So let's check the parentheses. So I'm closing the exponential, closing this first parenthesis, okay? And now I need to have a comma here and the value of the second equation, okay? So the second equation is going to be minus G times C, that is x1, plus E times, and then the rest here is exactly the same as this term here, yeah, because they're exactly the same. So I can just copy and paste this part here, yeah? They have a term in common, right? Yeah? Okay? Okay. Good? Yeah? Okay, and then the rest now, right? Oh, oops, I typed something wrong. Yeah. Okay. Now what do we have to do? We have to set the list of parameters, okay? So let's do this thing here. Commenting the order over here. Okay, so parse will be, so R, as I told you, I can just set it to 1 because this sets the times AO. And K, the carrying capacity, I can also set to 1 because this just also sets the population densities AO. Could be any value whatsoever, okay? Now B, what is B, right? B multiplies R, right? Just R, okay? So this is also related to a population scale, right? Yeah? Okay, since the carrying capacity is 1, this could also probably is going to change for something close to 1 as well, right? So I start with 1 here, but then this is the one, B is the one that we are going to, oh, I'm sorry, I'm talking something wrong here. Now it's the time of A, sorry. This is A now, not B. A, what is A? This is a hard one. Okay, this A here is the amount of prey you are consuming for in relation to the predation rate. Yeah, so I think this is the more tricky one. So let's do this last, okay? I don't know, do you have any suggestion already for what we should set A? I think this is a bit more complicated. So let's do this last, okay? Let me just open, leave A here without anything. Yeah. Now B, right? So B is multiplying air, and air is of the order of air incapacity, so B should also be of the order of 1, okay? So this, I'll put 1 for now. We can change this later. Now G and E, we already know that G has to be smaller than E, and G is death rate of the consumer, right? So death rate of the consumer, usually we would expect what? That it's of the same order or lower than the growth rate of the resource, right? Or something of this order, right? So, so a good first attempt here could be something like, I don't know, a half or maybe 0.1 or 0.2 or something, because the 1 is the growth rate of the resource, right? So D should be more or less the same kind of magnitude, okay? Of course, there are some systems where this is very different, right? But just for a first guess, right? You want to, this stuff should be the same order, okay? Okay, and now E, I just know that E has to be larger than D, right? Has to be larger. So let's put it maybe at 0.2, okay? So double, so the maximum growth rate of the consumer is double its death rate, okay? Something like that. But it's larger, but okay, for now, this is it, right? So now since E, now I just set it to 0.2, okay? Now A, I can think of A in terms of E, okay? So E, so this is the amount consumed, okay? Well, this is how much of the consumer there is due to predation, of growth rate due to predation, and this is the amount of prey, right? So the relationship between E and A, right, gives me the scale, the relative scale of population between predator and prey, right? So if you're measuring this in biomass, then usually E is going to be like 20% of A, right, in terms of, because of energy constraints. But if you're measuring this in individuals, this is much harder to get our head around, right? So, but thinking in terms of biomass, for instance, A should be 5 times larger than E, right? In terms of biomass, right? Just because of energy relationships. So, yeah, you have discussed this in terms of the predator-prey relations, yeah, or not? This idea that in terms of biomass, you have some efficiency and so on, yeah? So this is yeah, if you don't know about that, you can just guess, right? But what I'm doing here is something that is learning how to guess, okay? Yeah, this gets easier with experience, okay? I'm not saying that you should all think of this every time and so on. This is not, but this is how I did it, yeah? Okay, so I put here A, I'm going to put it equal to 1 also, okay? And then I have now all of our parameters here, okay? And with that, I can set now the initial condition. So initial condition, I'll put just, I put 0, 1 for both of them. I know that they should be close to 1, right? Or smaller than 1, because 1 is the carrying capacity for the prey, right? And now the times here, I will once again just guess between 0 and 50, okay? Again, because the growth rate here is 1, right? So 1 is kind of 1 generation, okay? So 50 is like 50 generations, I don't know, something like that, right? So, and then the solution X will be OD int with this equation RC, with these initial conditions, with this time, with this set of parameters, okay? And then I plot it, okay? Plot TX, okay? Let's put a label for time. Oops. A label for populations. This really deserves populations. This one really deserves legends, right? Because there's predator and prey, or resource and consumer in this age, right? So resource and consumer. right? And also let me put a grid over here. Yeah. Okay, so let's run this and see what happens. Okay, here what happened? We clearly see, you see the resource increases, goes close to 1, and then it starts to decrease, and the consumer is starting to increase. Here we clearly see that we didn't run for time large enough because the populations are still changing, you see? So what do? I increase the times, right? So I go here, I go from 50 maybe to 100, I don't know. 200, yeah, 200 is already stabilizing, but maybe a bit more, right? Yeah, so let's go to 500 here, okay. Okay, so you see, we found a fixed point, right? Yeah. Okay, so it kind of makes sense, right? So let's see what happens with a very small b, right? So because b is the parameter we are interested, right? So if I put instead of 1, we put equals to 0.1, okay? At 0.1, the consumer goes extinct, right? So with a very small attack rate, the predator doesn't get enough to eat, it goes extinct, right? What happens for a large bee? So instead of 1, I go now for 5, I don't know, right? Now we have predator-prey oscillations, yeah? So you see that we are already in a range where all these behaviors show up, okay? We have the extinction of the predator for low values of B, fixed point or existence for intermediate values of B, and predator-prey oscillations for large values of B. So what remains to be done, I have to run over all these values of B, right? So, and I already kind of have a range here because I start at 0, and I know that at least going up to 5, I already have oscillations, okay? Questions? Yeah, this looks simple. This is the kind of thing that it looks simple when I do it, right? Because I have a good feeling, a good gut feeling already, a lot of experience of how to choosing this list of arbitrary parameters, right? I know that I can just put R to 1, K to 1, I can guess G and E and A and so on, and it kind of magically works, right? But this, what will happen with your own problems? You are going to have a lot of time spent guessing parameters and finding some range where this stuff works like that, okay? Yeah? Okay, okay, so let's do now the bifurcation diagram. Do you have questions, people? Comments? This was easier than when I do it, yeah.
Second value of,
sorry?
What was the second value of B that you put it?
Sorry, didn't understand.
The second value of B. You changed it after to the display.
Ah, the value of B. Okay, so I started with B equals to 1, and then I decreased it to 0.1, and now I increased it to 5, right? How do I choose these values? I just guessed it, okay? I took a very small and then a very large, right? And how do I know that 0.1 is small and 5 is large? Because of units, okay, units. So B multiplies R here, and this BR should be non-dimensional. So dimension of R is related to carrying capacity. K is 1, so R is close to 1. So 0.1 will be small, 5 will be large. All right, so this is, yeah, again, when I do this, it looks very simple, but in your own problems, it will be harder, okay? But yeah, this is just with experience, you learn to recognize this stuff, okay? Okay, okay, then let's then do the bifurcation diagram, yeah? So let's copy the one over there again. So here it is. Over here, so I'll put this into a new cell down here. Okay, so now I'm going to change B's. Okay, so I put something, BB over here. I'm going to go from 0 up to 5. We can see later if 5 is okay, if you want more. Some 50 values then is time steps of, or B steps of 0.1. Now, what should be a long time here, right? So I went here up to 500, okay? Maybe this is okay, but let's put it 1,000, right? 1,000 time steps. I'll put maybe, yeah, here the time step for the time here, when you have cycles, you have to be careful to not have too large time steps, otherwise you won't see the peaks and valleys, okay? So it cannot be too large over here. Maybe let's go back to 0.1 here, okay, 0.1, okay? Now the initial condition, I will keep using 0.1, okay, because it was, the values here were oscillating about between, you see, 0.4, 0.2, 0.4, 0.6, okay? So 0.1 is, looks okay with 0.1, right? So 0.1 again, right? And now I loop over the values of B. Okay, so for B in BB, I have the list of parameters, so let me copy the list of parameters over here.
What are you doing now?
I'm drawing the bifurcation diagram, yeah? So we have already parameters that look promising, right? And I'm just going to go over many values of B over here. So B here instead of 5, I'm going to loop over this range of values of B, okay? And plot the bifurcation diagram, yeah? Okay. And now I solve. This equation is now called RC, okay? RC? RC, yes, RC over here. RC. I don't need all those elements. And now, now I need this x is equal 0 because I have two equations again, so I have to go for the minimum for each of the columns. For how many time steps, right? So I have, I'm running up to 1,000 time in steps of 0.1. So if I just look at the last 100 in time, okay? So I need, in time steps of 0.1, I need 1,000 points, right? 1,000 points. So I use, yeah, 1,000 here, it's okay. Right, and the same thing here for the maximum, okay? For the maximum, then I convert this to an array. And now I can look, it's already run here, it was kind of quick. And then I take the plotting code, the codes for plotting, okay? So let me use this stuff here. Okay, going back down there. For plotting, now I plot all of this as a function of B's, okay? The legends are already right? So this is resource and this is consumer. This in the x-axis is B. And let's see what happens. Yeah. Very nice plot, huh? Yeah? So at the beginning here, I have that resource is at 1 at its carrying capacity, and the consumer is extinct. Now, for some value of B here, lows to 0.8 or 0.7, I don't know. You see here that there's a small step here. You see, this is probably because I don't have a lot of points, so maybe I should plot this with more points, right? Or maybe I didn't wait long enough for this to do it. I'm not sure. Okay. But then we start to have an equilibrium fixed point with the two populations, right? You see that resources are decreasing in their equilibrium and consumers increasing. And then at some point here, close to almost 3, right? You have a bifurcation where now you have oscillations, okay? Now you have oscillations, you have predator-prey oscillations for these values of B over here. Yeah? Sorry? One at a time, sorry.
Can I see the initial condition again?
Which initial condition? So I just put 0.1 and 0.1 again.
Okay.
Yeah. I think it doesn't matter, okay? We can run again with 1 and 1, and it's probably going to be the same, yeah. But this is a good test, right? So you can, okay. Funny. Question. Let's go back in a moment for this, yes?
Sorry, can you go back to
The parameters.
No, just the rest.
I can hear you, sorry.
Can you go back to the graph code?
The plotting. Yeah,
Yes, the
okay,
plotting.
here.
Thank you.
Okay, so I'm plotting the y min has 2 columns. One is, let me print it here, right? So, oh, no, not here, because then it will run everything again. So this has 2 columns. One is the minima of the resource, and the second one is the minima of the consumer, okay, the predator. Okay, so I'm plotting here the minimum of the resource and the maximum of the resource, both of them in green, okay? So this is the minimum and the maximum in green, and then I take the second column, the minimum of the consumer and the maximum of the consumer, both of them in blue, right? So they show up in the same color, okay? This is why I specify the color, so I have both of these lines with the same color because they both are related to the consumer. Okay, if I don't put the colors, it should give you 4 different colors. That's not nice. Yeah, I don't know. Yeah, question. What is the question? Or is that okay? Yeah, yeah. Okay. More questions before I address this ugly thing here? Questions, comments. Do you feel more confident that you can do this by yourselves in the future? I think you're probably going to use this in your own very near future, right? Yeah. Yeah. So the hard part that it can be confusing is really choosing for which are the values of the other parameters, right? But then this is sometimes involves a lot of guessing, a lot of trial and error, okay? That's unavoidable, yes.
Can you go back to the code where you define
Which part?
Where you define the function? Yeah, that part. Yeah.
The bifurcation diagram itself,
Yeah,
the loop,
yeah.
okay.
Something went wrong in mine.
So I'm looping over the values of B, okay? So BB is this range. I go over each one of them, and then I redefine the parameter set to have this value of B, so be careful with the order, right? And then I pass this new set of parameters to OG int, right? And Y0, the initial condition was defined up here. The times are also defined up here. And here I have this mean with x is equal to 0 to look over the columns, yeah. So found the body? Found the body or?
Forgot to put B in the parameters.
Okay.
I left the value.
Okay. More questions, more comments? No? Okay, so we still have a couple minutes. Maybe let's see, because I told you, well, it doesn't matter the initial conditions, right? And then I did something, and then this this thing happened, right? So well, how do I look at this, right? So we go back here to, so we choose, for instance, I don't know, B equals to 4 point something here, 4.5, okay? But then with these initial conditions, with 1 and 1, okay? And let's see what happens, right? So instead of 0.1, I start with 1. And so sometimes you have to do this, right? You have to go back and see the plot of the solution again, right? So I simulate this. It looks okay, right? So the time that I used there was going up to 1,000, right? I don't know if this... Yeah, funny, yes.
Maybe put the bifurcation diagram in a log scale so we can see if it's going too close to 0 or something.
No, I didn't put it into a log scale, right? This
No,
is
it's
linear
a suggestion.
Scale.
It's a suggestion. To
Yeah, but the main issue here is that, let me delete this one here. So the main issue here is that when you see that there's an OG int warning, right? That there was excess work done by the integrator, okay? So this is something that I want, this is, to solve this you have to go into details about the OG-int function, okay? But this means that there was difficulty with the OG-int to numerically integrate the equations, okay? But it's funny how, yeah, how this changed over here. So maybe it's a little bit over 4.5, I don't know. Or maybe I use it too long time, so 1,000. I want to see if I can find this in the plots, okay? Maybe if I do this. Ah, here, you see it. This is wrong, right? So this is wrong, okay? And you see that I received this message here, okay? So yeah, we managed to break the integrator, okay? Yeah? So this is something that happens sometimes, right? So of course this is a nonsensical solution, yeah? Because the population goes to a negative value and then it just keeps growing. It's weird, right? So of course we know that if we just change the initial condition, this behaves better, right? You see, now it's okay, right? But why does, with this value here, it's weird, right? Usually it's because in the very beginning, right? So instead of plotting, of looking up until time 1,000, I'll just stop here at 50, okay? At 50, the problem already happens, okay? So let me go back here, 50. Okay, you see this, right? So what is this AO here? This is 10 to 298, right? So something goes to infinity here, okay? So around here, right? So we can even plot this in a log scale. What is AO log, right? So this means that the numerical integrator, okay, but there are negative values, then this doesn't work, sorry. So this will not help, right? So there are problems here, right? So how do you deal with this, right? So this is a whole new class actually, right? But then there are several ways to, you can either change the initial conditions, but you can also change parameters for the OG-int function, okay? So you see here that it tells that too much work was done, right? So you can, for instance, increase, yeah, I probably need to dedicate a lot more time to it, right? So increase the number of steps that you can take here. This sometimes solves the problem. Sometimes you, instead of that, and also do I have to go over a lot more detail. Okay, I think this solved the problem. Let's see. Yeah, this solved the problem. Okay, I'll go back to this at some other time to see, because this is a practical problem, right? Sometimes OG-int doesn't solve the equation correctly. Okay, it gives you this kind of issue. Okay, and then there are several ways you can, several methods to, or several options to OG-int to make it work harder at the equations to solve them. Okay, but I think this is a topic for another time. All right, so this buddy thing that we saw down here is because the solutions were not right, okay? The solutions, you had problems with the numerical integrator, okay? Okay, people, so everyone's happy, yeah? Yeah, okay, so do you want more exercises on bifurcation diagrams, or everyone has its own exercise in your own projects? Perhaps I can send another one later, okay? Okay. Okay, good, thank you.